section, we're going to be looking at systems of linear equations in two variables. So kind of taking a break from some of the other stuff we've been doing. You should have some flashbacks to previous math courses because when working with systems, this goes all the way back to what you would have learned in Algebra 1. And so I want to show you some things, I want to talk about some things, but at the end of the day, we're only going to do two different ways to solve a system. So before we get going, let's kind of talk vocabulary. There are three types of systems that you might encounter in terms of answers. The first one is an inconsistent system. It has no solution. Notice the two lines are parallel and will never intersect. So one type of way of solving a system is to graph it. You physically look at a graph and find where they cross or where the answer would be. So you can see here, these two never cross, they're parallel lines. This means it would be an inconsistent system. It would have no solution. In working the homework, you would say D and E, that the answer does not exist. Then there's an independent system. It has exactly one solution, and notice its answer is an ordered pair. The point where the two lines intersect is the only solution. So we have the option of no answers, one answer, or a dependent system, which has infinitely many solutions. The lines coincide, and they are the same line, so every coordinate pair on the line is the solution to both. So for the first one, your answer is going to be such as a D and E. Your second one is going to have an answer of an ordered pair. And your third one will have an answer of either all real numbers, or in the homework, it'll have you enter the one equation that they both are, because you can see this is only one equation that they would be. So that might just have you enter x and then like a 2x plus 4 for the y. So those are going to be the three different kinds of systems that we work with. Now, we don't use a graphing calculator in this course, and so we are not going to focus on the graphing end of it, because you can see in trying to find the answer of, say, this one right here, this is a crazy number, like 7 over 5 and negative 11 over 5, so I don't want to even hand graph this, and there's no way I could have hand graphed that and found that exact answer. And so we're going to really focus more on two other ways of solving system algebraically, because we're in college algebra. We're not just going to work with the graphing tool of just intersecting them and finding that answer. But before we can get into any of all that, we need to determine if an ordered pair is a solution. Basically, we want to figure out how do we actually check our answer to see if this solution is going to work. So here's our process. One, we're going to substitute the ordered pair into each equation in the system, then determine whether the true statements result from the substitution in both equations. If so, the ordered pair is a solution. This takes us all the way back to the beginning of the course when we were working with just plugging in values and getting true or false statements. Now here's the deal with this. If I want to check whether the ordered pair 5, 1 is a solution to the given systems of equations, then it has to be true for both. So this is my x and this is my y. I'm going to plug those in. So it would be 5 plus 3 times 1 equal to 82. I'm going to solve that out. So 5 plus 3 is equal to 82. So 8 is equal to 82, and that is not true. So it does not work for this first equation. So really it's irrelevant if I check the second one because it has to be true for both. Now for note's sake, I'm going to go ahead and plug it into the other one and show you that one. So it gives me negative 4 equal to 1. Again, that didn't work for that one either. So this one is definitely not a solution. Looking at the next one, it says determine whether the ordered pair is a solution to the following system. So again, this is my x and this is my y. I'm going to plug it in accordingly. 5 times 8 minus 4 times 5 equal to 20. That gives me 40 minus 20 equal to 20. So 20 equals 20. Check. That is a true statement, so check. It works for this one. Now, this is where the trouble lies. You can't just go, oh, look, it worked in one and move on with your life. You have to check both of them. So 2 times 8 plus 1 is equal to 3 times 5. That gives me 16 plus 1 equal to 15. Ugh, darn. This gives me 17 equal to 15, which is not true, so it does not work for the next one. So yet again, this is not a solution. Again, I wanted to work this one, and I wanted to work both of these examples because I wanted to show you when they do not work. Now, then if I had gotten a true statement for those, that would be a solution. But again, this goes back to the earlier part of this course. We were just plugging in and checking answers. Now, all that's important because here's our process for solving a system by substitution. This is one of our ways we're going to be able to solve. And it says solve one of the following equations for one of the variables in terms of another. So we're going to solve for one of the variables. Substitute into the second equation and solve for the remaining variable. Step 3, substitute that solution into the original to find the first variable and write your solution as an ordered pair. Step 4, check your solution. So this very last step of checking, it's really great. I know working with some of the previous sections, we can't always check our answer, but what's really nice with systems is we can check our answer with systems and make sure it's true just by simply plugging in. You can see working these two examples did not take very long. So let's kind of apply this. It says solve the following systems by substitution. Now you can either follow the instructions, say, oh, look, it's substitution, and follow that way. But sometimes the instructions just say solve the system of equations. They just say solve. You've got to be able to analyze the problem and figure out what is going to be the best course of action for solving this. So when you're looking for solving substitution, step 1 says solve one of the two equations for one of the variables. If this had just said solve, what you would do is you would look at the whole problem and look for the easiest variable to get by itself. And I say easiest because like this y right here, it's positive, it doesn't have a coefficient. That is the best course of action or easiest course of action of getting it by itself. Because all I would do is come out here, I have negative x plus y equal to negative 5, and I would just add x to both sides. So that gives me y equal to negative 5 plus x. So I want to be able to solve for y. Now you can solve for x, or you can solve for this x or this y, but you can see in solving one of these, I'm probably going to end up with the fractions along the way. So this was the easiest one to get by itself. So this is what y is equal to. So I'm going to plug that in here. So it gives me 2x minus 5 times, instead of y, I'm going to say negative 5 plus x equal to 1. So step 1, solve one of the equations for one of the variables. We did that. Step 2, substitute the expression for this variable into the second equation, then solve for the remaining variable. You can see I have all x's now, so I'm just going to distribute. It gives me 2x plus 25 minus 5x equal to 1. I'm going to combine like terms, so it gives me negative 3x plus 25 equal to 1, and subtract 25. So it gives me negative 3x equal to negative 24, and divide. So x is equal to 8. Step 3 says substitute that solution into either of the original equations to find the value of the first variable. If possible, write the solution as an ordered pair. So once you get x to be 8, I'm going to go back up here. I'm going to plug it in and say y is equal to negative 5 plus 8. Combine that together and I get y to be 3. So my final answer would be 8, 3. Your answers are going to be in the form of an ordered pair. Now again, you can always check your answer by plugging back into the original two equations and see if you get a true statement. So not too bad. Let's do another one. Solve the following system of equations by substitution. So again, look for a variable that's easy to get by itself, and you can see x is already by itself. X is equal to y plus 3, so I'm going to plug that in right here for x. So I'll say 4 equal to 3 times y plus 3 minus 2y. I'm going to distribute, combine like terms, and solve. Distribute gives me 3y plus 9 minus 2y. Combine like terms gives me y plus 9. Now I'm going to solve for y. So I get y to be negative 5. Once you get one of your variables, plug back into one of your originals to find the other one. So it gives me negative 5 plus 3. So x is equal to negative 2. So my answer would be negative 2, negative 5. And again, check your answer and you can make sure that that's true for both of them. So substitution's not bad, but I might need another method. Like it might not always be easy for me to get a variable by itself. So that involves our next one. Now, your notes are a good resource for you, so I do have a lot of words here, but I'm going to narrow this down for you for your personal notes. So here's going to be our process. You're going to write both equations with x and y variables on the left side of the equal sign and constants on the right. So to simplify that, we're going to line up variables and constants. So I'm going to get everything in order, looking the same. Step 2, it says write one equation above the other, lining up corresponding variables. If one of the variables in the top equation has the opposite coefficient of the same variable in the bottom equation, add the equations together, eliminating one variable. If not, use multiplication by a non-zero number so that one of the variables in the top has the opposite effect of the same variable in the bottom. Then add the equations to eliminate the variable. Very in-depth there. To simplify it up, you want to create opposites on one variable, then add two equations together. Add the two equations together. Step 3, solve the resulting equation for the remaining variable. So I would say solve. Step 4, substitute into the original and solve for the second variable. So we're going to substitute and solve. And then step 4, check your answer. So here's where this comes into play. Elimination or addition. This is called either the addition method or sometimes this is called the elimination method. In working with this method, sometimes it's really nice to just be able to add them together and move on. It goes really quickly because you may not be able to get a variable completely by itself without having to turn everything into fractions. So we're going to work quite a few examples. I'm going to do different kind of ones. First thing you want to do is you want to line up your variables and constants. See your x's, your y's, your constants. Step 2, you want to create opposites on one variable. What I mean by opposites is, notice this is a 1 and a negative 1, such as a 2 and a negative 2, 10 and negative 10, so a number and its negative counterpart. Once you create the opposites, you're going to add the two equations together. So I see my x's are opposites. This is a 1 and a negative 1. I'm going to add these two together. Adding them together, my x's cancel, and I get 2y plus 1y, which is 3y. Negative 1 plus 3, which is 2, and then I can solve for y. So y would be equal to 2/3. Now don't freak out when you get fractions. Remember, fractions are okay. After you get one variable, just like we did in the previous process, we're going to substitute back into the original problem, one of them, and get our other one. So I'm going to take that 2/3 and plug it in here for y. So this gives me x plus 4/3 equal to negative 1. And then move that 4/3 over. So negative 1 plus negative 4/3 gives me negative 7/3. Again, it's okay to get fractions. Just use your calculator to help you out along the way. Now, always enter your answer as an improper fraction. I don't want to round these to 0.66666 because that's not an exact answer. But you can see with this addition method or elimination method, it goes really quickly on getting that answer and really minimum work. So let's do another one. Again, I'm going to follow my steps here. So in looking at this, what I want to do is I want to make sure my variables are lined up. X's, Y's, constants. Next, I want to make sure and see if I have opposites anywhere. Well, 4 and 2 aren't opposites. Negative 1 and 1 are opposites. Notice I'm not doing anything with the constants. I'm just looking at the variables being opposites. So now that I have opposites, I'm going to add the two together. That gives me 6x equal to 18. Solve for x, so x is 3. So this would be 3 comma something. Take 3 and plug it back into either one of the equations. I'm just going to go back to that first one. So I get, let's see, 12 minus y equal to 12, so subtract. So negative y is equal to 0. So y is just 0. And 0 is okay. Fractions are okay. So don't freak out if you get a 0. Zeros are okay in math. They're just not okay in your bank account. Okay? So you can see I wanted to do this one because I wanted you to see how, in these two examples, it's already set up for us to solve. Now let's do two where we have to do a little bit more work with it. Solve the given system of equations by the addition method. Okay, so first I want to make sure they're lined up. X's, Y's, constants. Then I want to make sure I have opposites. Well, 3 and 1 are opposites. 5 and negative 2 are opposites. But it'd be easy for me to create opposites here because there's only a 1 here. So if I take this equation here and multiply the entire thing by negative 3, that would give me negative 3x. I'm just going to distribute that in. Plus 6y equal to negative 33. I'm going to combine that with my top equation. So although I amped up the bottom one, I did that so that now I have opposites. That cancels. I get 11y equal to negative 44. And then I can divide. So I get y to be negative 44. Now go up into any of the equations you like to kind of solve for this. I'm just going to go ahead and go up into this one here. So x minus 2 times negative 44, excuse me, negative 44 divided by 11 is negative 4, equal to 11. So that gives me x plus 8 equal to 11, and then I can solve. So I wanted to do this one because I wanted to show you a problem where I had to kind of multiply one of the equations to create that opposite. Let me do another one. And in this last one, I will show you, I might have to amp up both equations to create an opposite. So looking at this problem here, x's, y's constants, I'm ready to go. I don't have opposites. So I'm going to create opposites here with my x's, and I'm going to do that by finding the least common multiple between 2 and 5. The least common multiple between 2 and 5 would be 10. So I'm going to multiply the top one by 5, which would create a 10x. I'm going to multiply the bottom one by negative 2, which would create a negative 10x. So distribute that. That gives me 10x plus 15y equal to negative 80. Distributing this gives me negative 10x plus 20y equal to negative 60. And now I can add those two together. So this would cancel, and I get 35y equal to negative 140, and divide. So it creates larger numbers for me to work with here, but no big deal because just using my calculator, I can do the arithmetic with this. So this gives me negative 4. Now when I use that negative 4, I'm not going to go back into one of these. I'm going to go back into one of the original equations to find my x. So I'm just going to go up back into this top one. I'll say 2x plus 3 times negative 4 equals negative 16. So 2x minus 12 is negative 16. And then add 12 to both sides, negative 4, and divide. So I get x to be negative 2. Now, although we had to do more work for this problem, this really is the best course of action, because even if we were graphing it, I'd have to solve both those for y, and I'd have fractions. If I tried substitution, I'd have to solve one of them for a letter, and I'd have fractions. So really, this addition or elimination method is really the best course of action for figuring this out. Now, all this being said, let's do some application problems. So I've got my substitution method, got my addition method. Now here's a good application problem. It says, given the cost function and the revenue function, find the break-even point and the profit function. So we need to learn, what do these two problems mean? Well, your break-even point when working with business functions is going to be when your cost is equal to your revenue. So whatever it costs you to produce goods is equal to how much money you brought in. You're at break even, meaning you're not losing money anymore. You're not making money, but at least you're not in debt. So you would take your cost function and say it equal to your revenue function and solve from there. Your profit function, meaning when are we actually going to make money? Like how much money did we make after we pay for our goods and after we sell them? Well, your profit function is equal to your revenue minus your cost. So kind of random we put it in here, but it does work really well with systems depending on what you're working with. But we did need to identify these two things. So first I'm going to find that break-even cost. So I'm going to take my cost function and I'm going to say it equal to my revenue function. I'm going to solve it out from here. So I'm going to subtract that 0.85x. Can't seem to write. It gives me 35,000 equal to 0.7x, and then divide. So this gives me a value of 50,000. So after I sell 50,000 units, I'm going to break even and no longer be losing money. But I want to figure out, when do I make profit? So to find my profit function, I'm going to take my revenue function, 1.55x, and subtract out my cost function, 0.85x plus 35,000. So distribute that negative. That gives me 1.55x minus 0.85x minus 35,000. So my profit function is equal to 0.7x minus 35,000. So kind of a break from systems, but still into the applying of this depending on what we would have to do next with it. Now the last example I want to do is I want to create a system of equations, and then I want to solve it with you using one of our two methods. So it says the cost of a ticket to the circus is $25 for children and $50 for adults. On a certain day, attendance at the circus is 2,000. The total gate revenue is 70,000. How many children, how many adults bought tickets? So I need to create two equations here. I have children and adults, so however many variables you have is how many equations you need in order to solve them. So the cost of a ticket to a circus is $25 for children, so I'll have to take $25 however many kids I bring, plus $50 times however many adults I bring. The attendance at the circus is 2,000, so I would add up my kids plus my adults, and I should get 2,000. So this is one equation, and it's dealing with the quantity of how many people. The gate revenue is 70,000, so 25 times my kids plus 50 times my adults should total that 70,000 I brought in. So my second equation is going to deal with my cost or my money. Now that I have two variables I'm looking for, I have two equations. I can solve by either method. I'm going to solve this one by the substitution method because I can see I can easily get kids by themselves. So I'm going to subtract a from both sides, so I get children, is equal to 2,000 minus a. And then I can take this and plug it into my other equation. So I get 25 times 2,000 minus a plus 50a equal to 70,000. Distribute. That gives me 50,000 minus 25a plus 50a equal to 70,000. Combine. And then solve for a. So I'm going to subtract 50,000. I get 25a equal to 20,000. Divide by 25. So a would be equal to 800. Now, no big deal. Again, the hard part about this one was setting up your two equations. The rest of it was just substitution and being careful with my numbers. Now that I have that, I can plug it back up here into my children equation. So that would be 2,000 minus 800. So it gives me 1,200 for children. So how many children attended? Children, we had 1,200. And how many adults? Adults, we had 800 that bought tickets. And so I wanted to do this application problem with you. You will have one like this in your assignment and on the quiz for the systems part. So I hope this helps. Please contact me if you have any questions along the way.